Hello everyone, my name is Asawa. I'm from group 18 and here are my group members, Vandat and Lena. Today I'm going to talk about the project 8, reinforcement learning with CartPole. Now, let's get started. The first part of the project is about the reinforcement learning with CartPole V1 and environment overview and deep queue network design. The first thing I want to show here is the CartPole V1 environment overview. The CartPole V1 is a widely used benchmark problem in reinforcement learning. The environment consists of a cart that moves along a one-dimensional horizontal track with a pole attached to the cart by a hinge. And due to gravity, the pole is unstable and will fall unless controlled. The agent must continuously apply forces to the cart in order to keep the pole balanced. The next thing is about the objective of the CartPole V1 control test. The objective here is simple but challenging. The agent aims to keep the pole upright for as many time steps as possible. At each time step, the agent observes the current state of the environment and selects an action. The longer the pole remains balanced, the better the agent's performance. The next part is the state representation in CartPole V1. To make decisions, the agent relies on the state information provided by the environment. The state is represented by four continuous variables: the car's position and velocity, as well as the pole's angle and angular velocity. These values fully describe the system's dynamics and updated at every time step. Because the state values are continuous, this makes the learning problem more complex. About the action state and reward functions, based on the observed state, the agent can choose between two possible actions. Pushing the first is pushing the cart to the left, and the second one is pushing the cart to the right. The reward function is designed to encourage stability. The agent receives a reward of 1 for every time step that the pole remains upright. And the episode ends when the pole falls beyond a safe angle or the cart moves outside the allow range. And next part is about the limitations of traditional queue learning. The traditional queue learning methods store action values in a table. However, the CartPole V1 environment has a continuous state space, and there are infinitely many possible states. This makes it impractical to use a queue table. Although the discretization is possible, it reduces precision and learning efficiency, which motivates the use of deep learning approaches. And the next part is deep queue network approach. To overcome these limitations, we use a deep queue network, or we can say it DQN. Instead of storing queue values in a table, DQN uses a neural network to approximate the queue functions. Given a state as input, the network predicts the expected future reward for each possible actions. This allows the agent to generalize its learning to states it has not seen before. And before going to the next part, I wanna show to you guys the ReLU activation functions. The ReLU or the rectified linear unit is defined as the maximum between 0 and the input value. This means the negative inputs are set to 0, while positive inputs pass through unchanged. Rarely introduce non-linearity into the neural network, which is an essential for learning complex relationships between states and actions. It also helps reduce the vanishing gradient problem and allows the network to train faster and more stably. And now I'm gonna show you the last part, which is DQN architecture and action selection. Using the value in the hidden layers, the deep queue network is implemented as a fully connected feed-forward neural network. The input layer receives the four-dimensional state vector from the CartPole V1 environment, and the network contains 2 to 3 hidden layers, each applying ReLU activation. The output layer produces one Q value for each possible action, and finally, the agent selects the action with the highest predicted Q value, which represent the best expected long-term reward. So this is the end of my part, and the next part, my partner Lena will discuss about that.
Hello everyone, my name is Chen Linam and I will talk about the key reinforcement learning mechanisms. First thing you need to know about is experience replay buffer, the definition of it and the motivation behind it. The experience replay is a technique in deep reinforcement learning, for short is DRL, designed to improve training stability and efficiency by storing and reusing past interactions between the agent and the environment. The experiences are stored as tuples by state, action, reward, and next state. Instead of learning only from recent transitions, the agent samples from a replay buffer. Uh, Next is prevents unstable learning caused by sequential and correlated data. The motivation behind it is training on consecutive experiences leads to biased updates and unstable convergence. The structure of experience replay buffer is described as the experience replay buffer is implemented as a fixed capacity memory that stores transitions in the form of st, a of t, r of t, and s of t plus 1. Each new transition is appended to the buffer as the agent interacts with the environment. When the buffer reaches its maximum capacity, older transitions are discarded. This structure allows experiences from different time steps and policies to be reused efficiently during training. Moving on, we can learn with replay buffer samples. Instead of learning from the most recent experience, the agent samples random mini batches from the replay buffer to update the deep queue network. The learning update minimizes the temporal differences. Error defined as the loss function equals the expected square temporal difference error between the Bellman target and the current queue value. This batch-based update process decouples learning from real-time interaction and results in smoother convergence. The next concept we have is the epsilon greedy exploration. The definition of epsilon greedy is a stochastic action selection strategy used in reinforcement learning to balance exploration and exploitation. It is defined as a policy in which the agent selects a random action with probability E and selects the action with the highest estimated Q value with probability of 1 minus E. This definition ensures that the agent does not rely solely on its current value estimates, which may be inaccurate early in training. In practice, epsilon greedy exploration prevents premature convergence to suboptimal policies while still allowing the agent to exploit learned behavior as training progresses. The, Under the epsilon greedy strategy, the agent selects a random action with a probability E and selects the greedy action with probability of 1 minus E. Formally, the policy is defined as T equals to the combination of random action with probability E and the argmax of A Q of ST and A with probability of 1 minus E. This ensures continuous exploration while allowing the agent to exploit learned knowledge. To improve learning efficiency, the exploration rate E is initially set to a high value and gradually reduced over time. A common decay formulation is the E greedy exploration rate equals to the maximum between a minimum exploration value and an exponentially decayed initial exploration rate over time, which encourages extensive exploration early in training and increased exploitation as learning progresses. These decay mechanisms helps the agent converge to a stable policy. By combining these two, we reach to the final destination of is combined effect on learning stability. The epsilon greedy exploration ensures that the replay buffer contains diverse experiences collected from different states and actions. The experience replay buffer then randomly samples from these experiences, preventing the network from overfitting to recent interactions. Together, these techniques stabilize learning and improve sample efficiency and enable reliable convergence in deep Q learning.
Okay, have a good day, everyone. I'm Vandat, and we are Group 18. And today I will talk about our final project. Is the reinforcement learning with CartPole. So my part is deep quickness work for CartPole V1, research on reinforcement learning in continuous environment. Now let's talk about our solution. Why did we chose the QN instead the classical query learning? The problem lies in the continuous state. In classical query learning, we use a query table to store value, but since the position and velocity of the card can be any decimal number, the number of states is infinite. A query table is impossible to use here. Our solution will replace the table with a natural network. The network acts as a function approximator. It takes that state as input and estimates the query values for moving left or right. And next is network architecture and replay memory. Here is a closer look at our architecture. The network, we design a simple fully connected network. It takes four inputs from the state and produce two outputs. Experiment replay. This is a crucial technique that implemented in reinforcement learning. Consecutive data samples are highly correlate. If we train the network on a sequential frame, it might overfit or forget previous experiences. To fix it, we store the agent experience in the replay memory. During training, we randomly sample a bunch of experiences. This breaks the correlation and makes the training much more stable. Next is next is experiment and results. Moving on to the training process, there are two key components I want to highlight. First, the load function. We use smooth L1 loads, also known as hyperloads. We show this over mean square error because it is less sensitive to outlier. When the error is very high, hyperloads is linear, quick prevent exploding gradient. And the second, exploration versus exploitation. We use to epsilon with this strategy. In the beginning, epsilon is high 90%, so the agent explode randomly. Over time, we declare epsilon to 5% for forcing the agent to exploit the policy it had learned. Okay, that's the experimental result. Okay, uh, I will show uh, I will show something about our practice and okay. This chart serves as our quantitative proof of a concept. It confirms two key metrics: learning rate, how quickly the red line moving over it escapes the random exploration phase, and stability, the agent's ability to maintain an average reward about 100. 95 consistently with officially deemed the CartPole task as shown and this and this is a video render demonstration. The video will visually highlight two critical aspects of our solution. That is the agility and control. The agent precedes rapid action, left-right push, in response to the smallest change in the pole angle and velocity, and reverse left, the subtained balance, demonstrating that the agent had generalized the balancing procedure effectively, not just memorized a few steps. Okay, okay, so okay, so to conclude our project, such as the QN agent successfully shows the CartPole V1 environment with a continuous state and limitation. We found that the algorithm is very sensitive to hyperparameter, es- especially the learning rate. A small trend can cause that agent to fail completely. And future work to improve it, we suggest implementing double DQN or dueling DQN to reduce over dimension errors. We can also apply this logic to reward information system problem like server loss balancing. Okay, okay, so that brings to the end of our presentation. Thank you for listening.